Hi everyone. Before we get started, please can everyone put their student number in the chat so that we can use that for attendance. Okay, I see there's 28 people, so I'll wait for that to pop up in the chat and then we can get started. Okay, I hope everyone put their student number in the chat for attendance. Okay, so today we're going to go through the idea of definite integrals, their properties, and how we evaluate them. So firstly, how is the definite integral defined? Okay, so remember way back at the beginning, we looked at the problem of finding the area below a curve, and we came up with this idea of summing up the rectangles and making the rectangles very small, and then that gives you the area once you sum them up. So we use that idea to define the concept of a definite integral. In other words, the definite integral we write as the integral from a to b, f of x dx. We write this, but what we mean is the limit of a Riemann sum. So this is the limit as n goes to infinity, the sum from I equals 1 to n, f of x r delta x. Okay, where this part over here, this was the Riemann sum. Okay, so we take the limit of a Riemann sum and we get the definite integral. Now, we know from the fundamental theorem of calculus that this definite integral can be written in a different way. So this top part was the first way we saw it. The second way is to take f at b minus f at a, where this f at b and f at a, those are functions evaluated at the bounds, but they're very special functions. They are any antiderivative of f. Okay, and we said that, remember, antiderivatives only differ by a constant. So if you have an antiderivative of f and I have an antiderivative of f, there's only a constant addition that is different between them. So we said when using definite integrals like this, we can take the constant to be 0. So we can take c to be 0. Okay, so we're just choosing a particular antiderivative. So if we look at this first example here, if I want the integral from 0 to 1 of x squared dx, to evaluate this, we're going to use the fundamental theorem of calculus. So we need to find any antiderivative. Now we know that one particular antiderivative is 1/3 x cubed. Now 1/3 x cubed plus 5 is also an antiderivative. But to make things a lot easier, we just take that constant to be 0. So we don't have to worry about adding those. So this is going to be this is how we write it, as 1/3 x cubed. So this is our antiderivative, capital F. Okay, where we just chose the constant to be 0. And we need to now evaluate this between 0 and 1. Okay, so 1, that is our upper bound B, and 0, that is our lower bound A. So this now becomes 1/3 evaluated at 1 cubed minus 1/3 evaluated at 0 cubed. So we end up with just 1/3. Okay, just before we carry on, if there's any new students that have joined us, please make sure that you put your student number in the chat so that we can use that for attendance. Okay, so we don't have any way of acknowledging that you've attended unless you put your student number down. So please ensure that you do that. Okay, so it's your responsibility to put your student numbers down. Okay, so that's how we evaluate these definite integrals. We look at the function, whatever the function is, we find the antiderivative using whatever rules, we will get to those, and then you have to evaluate this antiderivative at the bounds. So evaluate it at the upper bound minus the evaluation at the lower bound. Okay, and that is the main idea behind evaluating definite integrals. Okay, but there are a few properties of definite integrals that makes this process easier to do. So let's have a look at those. Okay, so properties of definite integrals. That can make calculations easier. Okay, so if you use these properties, you should be able to make your calculation easier for yourself. Okay, so let's have a look at some of these properties. Okay, the first property is that if you have the definite integral from a to b dx, this is equal to b minus a. Okay, that's the first thing. So you can imagine that there is an imaginary 1 here. Okay, if you want to think about it like that. So if you're integrating the constant 1 function from a to b, then that just gives you the width of the interval. Okay, so this pops up sometimes when you have to integrate just dx or integrating 1 dx, however you want to think about it. Okay, that just gives you b minus a. Number 2, if you have the integral from a to b, some constant c times f of x dx, then this is equal to c times the integral from a to b, f of x dx. Okay, we say that we can take the constants out of the integral. So if it's c times a function, you don't have to calculate the antiderivative with c. You can take c outside, like that. You do your integral, and then only afterwards you multiply by c. Okay, so sometimes that helps. If you have some constants multiplying your function, it's easier to take them out of the integral. Take it out of the integral, do all your working, and then multiply them afterwards. Okay, so sometimes that's helpful. Number 3, if you have the integral from a to b of f of x plus g of x, okay, if you have the sum of two functions inside your integral, then you can separate them into two integrals. Okay, so if you have the integral of a sum, then you can split it up into two parts and you can do them separately. So you can do the first one on the side, you can do the second one on the side, and then add them together afterwards. Okay, and this also works for the difference. So plus or minus here becomes plus or minus here. Okay, so that's the third property, separating integrals into multiple parts. Okay, are there any questions so far about these properties? Okay, and then the last property, number 4, this one is what happens if you're multiplying your integral by a negative number? Okay, or if you have a minus sign, anything like that. So the integral from a to b of f of x dx is equal to minus the integral from b to a f of x dx. Okay, so you can think about this property in two ways. Firstly, if you multiply by a minus sign, you swap the bounds. So let's just make a note here. Multiplying by minus 1 swaps the bounds. Okay, or if you want to think about it a different way, if you swap the bounds, then you need to multiply by minus 1. Okay, so that's just two ways of thinking about this property. Okay, so let's have a look at an example, just where you might use this property. Okay, so let's say we have the integral from 1 to 0 of x squared plus x dx, something like that. So let's just do it as is without using any of these, without using property 4. So we're not going to swap the bounds, we're just going to leave it like this. So this is going to be 1/3 x cubed plus 1/2 x squared from 1 to 0. So this is going to be 0, that does nothing. So 0 minus, and then we have 1/3 plus 1/2. So that's going to be 0 minus 5/6. Okay, so we end up with minus 5/6. And that's fine, you can do it this way. But what I noticed with some of your tests that you had for test 1 and test 2, this minus sign over here, a lot of you forgot to distribute the minus sign. Okay, and that's a big problem because remember, it's the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. And a lot of students see that the upper bound is 0. So you put down 0, then minus the lower bound, but then on the next line, that minus sign is missing. Okay, so I've noticed that in a few things, and there's a problem with that. Okay, you can't forget that. Okay. Before we carry on, let's just look at the chat, see if there's questions. Got a question here. Is the sum or difference of the same function for number 3? Let's have a look at the properties. For number 3, for the same function, no, these are different functions. So this is some function f plus some function g. So then you can separate it out into a single integral with f and a single integral with g. Sorry, I forgot that there. Okay, that's supposed to be a g. Okay, so if you have f plus g on the left-hand side, you can separate it out into one integral with f plus or minus another integral with g. Okay, another question here. You repeated f of x on number 3. Yeah, thanks for spotting that. Okay, and that's everything there. Okay, yeah, so that's supposed to be f and g over there. Okay, so let's get back to this. So over here, we did it this way without changing the bounds. And I just want to point out that there's this minus sign here that you can't forget about. Okay, so the minus sign from evaluating it at the upper bound minus evaluating at the lower bound, some people forgot that. Okay, so please remember that there. Now, let's try this doing the other method where we swap the bounds and put the minus sign out in front. Okay, let's have a look at that. So we have the integral, same one, from 1 to 0, x squared plus x dx is equal to, but now I'm going to swap the bounds. But I remember if I swap the bounds, I put the minus sign. So it's going to be minus the integral from 0 to 1. Okay, so it was from 1 to 0. I swapped them and I put the minus sign. X squared plus x dx. Okay, so now let's do this. So this is minus, we still keep the minus there. 1/3 x cubed plus 1/2 x squared from 0 to 1 equals, still got that minus there, don't forget that. So I'm going to have 1/3 plus 1/2. And now if I put 0, I'm just going to get 0. So I can just leave it like that. So just leave it like that. And that's going to be minus. So we're going to have 2 plus 3, that's 5/6. So you see, swapping the bounds, we put the minus sign, and the minus sign just stays with us the whole way down. You just do it once at the top and you forget about it. You leave the minus all the way through, no problem. However, over here in the previous one, you've got this minus here. You need to remember to distribute it inside. So this bracket over here that I underlined in green, you could have things being added and subtracted and all of that. You need to remember this in front. Okay, so sometimes people forget that, but if it's out in front, you just leave it all the way through and it stays there right to the end. You don't need to worry about it. Okay, question here, we're allowed to get a minus sign in our answer. Okay, so let me just make a big note about that before we move on. Minus signs in an answer. Okay, so number 1. Distances are never negative. Okay, if I ask you to find a distance and your answer is negative, you've done something wrong. Okay. Number 2, areas are never negative. Okay, if I asked you to find the area between two curves and you get an answer with a minus sign, you've done something wrong. Okay, areas are always positive. You're never ever going to get a negative area like this. Number 3, volumes are never negative. Okay, if you're using the disk method, the washer method, or the shell method, and you get a negative answer, you've done something wrong. Okay, so these 3 cases, distances, areas, and volumes, they are never, ever negative. You should never get a minus sign with those answers. Okay, anything else, you can get whatever. Okay, these 3 have to be positive. Any other question, it can be negative, it can be positive. It depends on the question. But these 3 specific ones, distances, areas, and volumes, always positive. So distances, areas, volumes are always positive. So you should always get a plus with your answer, never a minus sign. Okay, does that answer your question? Okay. Okay, awesome. So just remember these 3, always positive. Everything else, not worried about that. That depends on the question. Okay. Let's have a look at another example. Okay, so we have the integral from 0 to 1 of 4 plus 3x squared dx. Okay, we want to find this. Okay, let's just quickly look at the bounds. The bounds go from 0 to 1, so that's fine. We don't need to do any swapping or anything because the lower bound is smaller than the upper bound, so everything is in the right order. We don't need to worry about any issues with the minus sign there. Okay, so right away, we can find the antiderivative. So the antiderivative of 4, that's going to be 4x. The antiderivative of 3x squared, remember you add 1 to the exponent to make it 3, divide by 3, so that's going to be a 1. So we just have plus x cubed. We need to evaluate this from 0 to 1. So we get 4 times 1 plus 1 cubed minus, now if we substitute 0, we're just going to get 0, but let's just check. So we get 4 times 0 plus 0 cubed. So we're going to get 4 plus 1, that's going to be 5, minus 0. Okay, that's just going to be 5. Okay, so another straightforward example of finding the antiderivative and then evaluating the antiderivative. First at the upper bound, minus evaluated at the lower bound. And please note that this antiderivative has no plus c to it. Okay, we write 4 times 1 plus 1 cubed. There's no plus c mentioned anywhere. In this antiderivative here, no plus c. Okay, for definite integrals, we take c to be 0. So don't even write it down. It's just 4x plus x cubed. You leave it like that. When you're evaluating it here and here, again, no plus c. Okay, I've seen a couple students, they're putting plus c in the antiderivative in this first step, and they're putting plus c in the antiderivative evaluation for the second step here. Okay, you don't do that. There's no plus c anywhere for definite integrals. Okay, you only put plus c when you are finding indefinite integrals. Okay, we're going to look at that tomorrow. Okay, I see there's some new students that have appeared here. If you've just joined us, please make sure that you put your student number in the chat. Okay, for attendance, that is your responsibility to put your student number there. Okay, if you don't put your student number, we have no way of tracking if you have attended or not. Okay, so that's just another thing that I've spotted in test 1 and test 2. Some students are putting plus c for definite integrals. You don't do that. Definite integrals, no plus c. So definite integrals, no plus c. You just don't do that. Okay, any questions so far? Okay, let's have a look at some more. Okay, so these have been pretty simple so far. Let's do a nice summary of all the rules that you need to know when finding these antiderivatives. So here, the second step, when we take the antiderivative, depending on the function, there's different rules that you need to follow. Okay, so let's look at a summary of that. So summary of antiderivative rules. Okay, so remember these rules. We need to know them for that first step of integration. You find the antiderivative, that's step 1. Step 2, you evaluate it between the upper and lower bounds. Okay, so the first thing is the antiderivative of a constant. So if f of x is a constant, let's say c, then the antiderivative, all right, let's not use c, let's use something like k. Then the antiderivative, or the general antiderivative, let's say, general antiderivative will be capital F of x is equal to kx plus c. Okay, so this is the general antiderivative where we have plus c. If you are using this, if you're using this in a definite integral with bounds, you don't put the plus c. Okay, so we spoke about that on the previous page. Number 2, f of x is equal to x to the n. We want to find the general antiderivative. That's going to be 1 over n plus 1, x to the n plus 1 plus c. Okay, so you add 1 to the exponent, you divide by the new exponent. Okay, and this works for positive and negative exponents, except for -1. That's a special case. So I'll put that in red because that's a special case of number 2. We have f of x is equal to x to the -1, or we can write that as 1 over x. The antiderivative in this case, we don't use the power rule, because if we use the power rule, we're adding 1 to -1, so the new exponent becomes 0. That's wrong. You can't have that. So in this case, it's going to be the natural log absolute value of x plus c. Please do not forget the absolute value here. So it's the natural log absolute value of x. Okay, you can't take the natural log of a negative number. That doesn't work. So we need the natural log absolute value of x to make sure that the input is positive. Okay, so this is a special case when the exponent is -1. Okay. Number 4, trig functions. If f of x is equal to sine kx, we want to find the antiderivative. Okay, the antiderivative of sine is minus cosine, but we've got this extra factor of k, so it's going to be 1 over k with the minus sign, cos kx. Okay, much like if we have an exponent, we divide by the exponent. If we have a multiple like this, sine kx, you divide by that multiple. Okay, and then sine becomes minus cosine. Number 5, f of x is equal to cos kx. We want to find the antiderivative. Sorry, and then you have the plus c. The antiderivative will be 1 over k sine kx, and then plus c. Okay, so the antiderivative of sine is minus cosine. The antiderivative of cos is sine. And remember, if there's a multiplying factor on x, you divide by it. So the antiderivative of sine 2x is minus 1/2 cos 2x. Okay, you always divide by that factor. Okay. And number 6, if f of x is equal to e to the kx, then the antiderivative. Okay, so remember, the derivative of e to the x is e to the x. It's unchanged. The same thing here. The antiderivative of e to the x is e to the x. But if you've got some multiplying factor, we do exactly the same thing for sine and cosine. We divide by that factor. So it's going to be 1 over k e to the kx. Okay, you always divide by that. If you were differentiating, you would multiply by that factor, but anti-differentiating is the opposite. So instead of multiplying by the factor, you divide by the factor. Okay, so we have 1 over k e to the kx. Okay, so these are the special functions that we see all the time, and you need to be able to find the antiderivative. Okay, any questions so far about these? Okay, and then there's one more trig function that's useful to know. F of x is equal to sec squared of x. Okay, so the antiderivative of sec squared is going to be tan. Plus c. That one is very important to know for trig integrals, which we've just started from last week. Okay, and then number 8. F of x is equal to sec x tan x. The antiderivative in this case will be sec x plus c. And you can check that by just differentiating going the other way. So the derivative of tan will be sec squared. The derivative of sec will be sec tan. So you integrate going one way, you differentiate going the other way. Okay, so these are just a couple of ones that you should know, just off by heart. It really helps getting through the problems quickly, so you don't have to look anything up. So if you get the integral of e to the 2x, you should know very quickly that's 1/2 e to the 2x. Okay, we've got a question there.
So you say on number 6, aren't you gonna add plus C at the end?
Yes, that's right. Thank you for spotting that, plus C. Yeah, so whenever you find the general antiderivative, you always have your plus C. Okay, thanks for spotting that. Okay, any other questions on these? Okay, so I just want to make one last note here with these. So please learn these. So you don't have to look them up when doing problems. Okay, so looking things up, if you need to look these up in your book or textbook or online, it takes a lot of time to actually see what is the antiderivative of e to the 2x. But if you just remember this very short list, you should be able to do the problems much quicker. Okay, because you can just check, okay, I know straight away what this antiderivative is. Okay, it really helps with the time. Okay, someone's asking for cosec. Yeah, that's going to come later on. Yeah, so that's not part of this stuff now. This stuff is just to remember. When we do cosec and cotan and all of that, that comes later when we're doing U substitution and things like that. Okay, so we're not there yet. This is just the straightforward ones that I expect you to know off by heart. And then the ones with cosec and sec and tan, those require calculations. We will do that later on. Okay, so we'll save that for tomorrow or Wednesday. Okay, any questions about this list or anything that we've done today? Okay, so if you've just joined recently, please put your student number in the chat so that we can keep track of it for attendance. Okay, so I'll just give, I think there were a few people that joined. Please make sure that your student number is in the chat so that we have it for attendance. Okay, and then tomorrow we will look at indefinite integrals and how to evaluate those. So things like tan, cosec, cotan, sec, all of those that we will cover tomorrow. Okay, but if you do have any questions later on, please just email me or post them on the WhatsApp group. Okay, I can help you out. Okay, I'll see you tomorrow for indefinite integrals. Bye, everyone.